implicit differentiation. The difference explicit versus implicit differentiation. What do you think the differences are? If it's explicit, what does that mean? Precise, yeah. So with the explicit differentiation, we have y equals some function of x. So the x's and the y's are separated. Something like we did last time. We took the derivative of that. Oh, that's pretty limited. We are restricted to certain types of equations. But implicit differentiation allows us to open up infinitely more domains. This is where x and y are not separated. You can have x's and y's on both sides of the equation. Like something like that. 3xy equals sine xy. In other words, implicit differentiation is when you cannot separate, and you don't want to separate the x's and the y's. You take them with respect to the variables as you go along. That's what we're going to do in this section. We're going to look at these type of problems. So let's begin slowly. Let's look at the first example. Example 1 says, find the derivative, or dy dx, of this equation. What does the graph of that function look like? Because a parabola is that. Okay, if you square, okay, let's look at that. If we took this and we square root both sides, what do we get? Equals what? No. I know you're going to say that, but from algebra, try to think back of when you square root something with a square, what do you have to do? Right. Because, well, the way we did this in algebra, what can x be to make this thing true? It could be positive 2, or it could be negative 2. Same thing here. If I take a negative x and put it in there, I get x, square root of x. So we have to look at both of these. So let's look at taking the derivative of this one. Well, these two, I should say. So go ahead and take the derivative of those two. We have one of them is the positive radical x, and then we have the other one, which is the negative radical x. So take the derivatives of those. Because most aren't getting far here. What do you have to do first? Rewrite it as an exponent. Because we have the power rule. Now, when we take the derivative of it, we get 1/2 x and subtract 1 makes it negative 1/2, which makes it 1/2 square root of x. That's the derivative of the first one. We'll do the same thing with the second one. What's going to happen to that one? Yeah, it'll be the same thing because the negative is a coefficient. So that's how we did it up until now. And depending on how well you remember or do your work and stay current, it takes you some time. It shouldn't take you more than a couple seconds to do those questions by now. But I need you guys to stay current. Let's look at this is one way of doing it. Let's look at the way we're doing it using implicit differentiation. So we'll look at implicitly. So we have y squared equals x. The whole concept about implicit differentiation is when you take the derivative with respect to x, treat it as usual. In other words, take a derivative of x like we normally do. But when you take the derivative with respect to y, you take a derivative of it, and you must place a dy dx after it. So there's the big difference, is we take the derivative of x and y, but whenever you take the derivative with respect to the y variable, you have to put dy dx because y is a function of x. Let's see what this means mathematically. Take the derivative of both sides. What's the derivative of y squared? Two y. Is that it? Nope. Was that? What did I just write up there? What you guys just spent 5 minutes writing? You have to put a dy dx behind it. Whenever you take a derivative of the y variable, you have to put a dy dx behind it. What's the derivative of x? So to find the derivative, we have to isolate the dy dx. So we have to divide both sides by 2y. So the derivative is 1 over 2y. But what is y? Can we get a value for y? If you're bobbing your head, you should tell me how to do it. How? And do what with it? No. But you're right, we have to do that, something with that. What did we do earlier? Root, right. So take the square root. So that becomes y equals plus or minus square root of x. We have to solve for y. Now, anywhere I see a y, we put a plus or minus root x, which is exactly what we just found. 1 over 2 root x, negative 1 over 2 square root of x. Because you have a positive and negative. This one's positive, this one's negative. So that's how you do implicit differentiation. Okay, let's look at example 2 then. Hopefully, well, let me put a couple of other examples on there so you guys can start practicing how to do this. XY equals, oh, the example I put up there earlier. What you're going to be asked to do is to find dy dx, which is the slope. Again, it hasn't changed, never changed. Take the derivative of both sides. What do we have to do to take the derivative of this side? Which method are you going to use? Which one? Which one? Oh, yeah. Yes, it's exactly what it's going to be. I didn't hear what you said. Yeah, you drive absolutely correct. It's the product because it's x times y. So this is your f and this is your g. So the derivative of f of x is what? 1. The derivative of y is what? What else? Whenever you take a derivative of y, you have to put that dy dx behind it. Remember, y is a function of x. We get y times 1, which is y, plus x times 1 is x, dy dx. That's the left side. Now, the right-hand side, we just talked about that last class, taking the derivative of trig functions. We have to do the same thing here. But we're going to use a chain rule. Remember what the chain rule was? What? Are you saying the derivative of the trig functions? No, what's the chain rule? The chain rule is a function within a function. Do we have a function within a function? Yeah. We have sine of this product. So we have a function within a function. What is a chain rule? The chain rule says this. If I have, in this case, sine of u, take the derivative of the outside, which is what? Cosine, times the derivative of the inside. So this is going to be sine turns into cosine xy. That's the inside. That's the outside. Now we have to multiply by the derivative of the inside, which is, fortunately for us, we have it right here. Y plus x dy dx. Because it's a product. We have to do the product rule of that. Now what do you think we do? What are we looking for? We're looking for dy dx. So we have to get rid of all the parentheses, distribute what you have to, and get all the dy dx's to one side, everything else to the other side of the equal sign. So this side here is okay. So it's y plus x dy dx. But this side, we got to multiply. Y cosine xy plus x dy dx cosine. We got rid of the parentheses, distributed. Now we got to move all the dy dx's to one side. So let's move this over here. And whatever is not a dy dx goes to the other side. So we're going to have x dy dx minus x dy dx cosine xy equals y cosine xy minus y. Everybody follow what I just did there? This is one of the most complicated parts of this whole process, is once you get rid of all the parentheses, you have to get all, anything that has a dy dx in it goes to one side. Because anything you took derivative, because that's what we're solving for. Now we have to solve for dy dx. How do we get the dy dx by itself? So we do what? You're right. But we have to do what? What's the process called? Starts with an F. Factor, yeah. Because we're trying to get this by itself, and they're both of them in there, so we can factor it out. That leaves only x minus x cosine xy inside. Y cosine xy minus y. We're not done yet. What do you do next? Yeah, we have to get rid of this by dividing. Very good. So we have dy dx, x minus x cosine xy equals y cosine xy. Sheet away. So I divide both sides by x minus x cosine xy. Can we do anything else on this side? let's rewrite this one. Just so we have a number. So we have the top's going to be negative y plus y cosine xy. The bottom is x minus x cosine xy. Can we factor anything? On the top, we can factor out a negative y, which leaves us what? 1 minus cosine xy. And on the bottom, we can factor out an x, which leaves us 1 minus cosine xy. One minus cosine xy cancels. So dy dx is equal to negative y over x. That's the derivative. Let me think of another one here. Find dy dx. Okay, so let's do each of these separately. So the derivative of this one, we have to use which rule? Product. And 2 is a constant, so leave it out there alone. So we need to touch that one. So we have f is y squared. G is x cubed. F prime is what? Very good. 2y dy dx. And then the derivative of x cubed. It's a product, so we add. So it's going to be 2x cubed y dy dx plus y squared 3y squared x squared. That's the first part. Ever got that? Or no? I see. What part did you mess up on? Out in front?
Yeah.
Yeah, so there's 2 still out there. So I'll put it in front here. Because if you did include it in this one, you'd get what? You'd get 4y dy dx. So multiply this one by 2. The 2 we took out here goes to the first one. And what about the second one? Does it go to that one too? No, because when we split them up, this was my f and this was my g. So I have, so that's 2 times 3, which makes it 6. So that's the first part. Because this 2 is my f of x. Well, yeah, if you want to, you could always take it out separately if you want to, and then put it back at the end, or you could treat it as this part. But what if you don't include it when you do this, you have to multiply it back into the whole equation, because, or you could include it. See, that really doesn't matter. because it's a constant multiple. Plus, what's the derivative of this one? Which rule do we use there? Starts with a C, ends with ain. Chain. So the threes, leave it alone. What's the derivative of cosine? Negative sine. Y. Times the derivative of insight. The derivative of y is what? Dy dx. Equals the derivative of 4x is 4. So we can make it look nicer. 4x cubed y dy dx 6y squared x squared minus 3 sine y dy dx equals 4. So once we take the derivative of each part separately, we have to separate anything has a dy dx on one side, anything that doesn't on the other side. So what do we move to the other side? This one here, right? The middle term. Because the first term has dy dx and the last term has dy dx, third term, actually. Oh. So we're going to end up with 4x cubed. Let me rewrite the whole thing. So it's 6y squared minus 3 sine y dy dx equals 4. So that's just carry over. So now I move this over to the other side. Yeah. Oops. I'm missing a dy dx here. Four minus 6y squared x squared.
Why doesn't that one have a dy dx?
This one? No, because this part here was derivative of the x part. It was this part here. So we took the f function to begin with times the derivative of the x. I know you're gonna start seeing dy dx's everywhere. And so what do we do on the left side? Factor it out. Since you're trying to get dy dx by itself, factor it out. Minus 3 sine y. And the last step. Divide both sides by 4x cubed y minus 3 sine y. So there's my derivative. So what did we just labor to produce? What does that represent? But what does it mean? What is it giving us? Yeah, the slope of the curve at any point xy. So if we want to know, because this is going to be an ugly curve to begin with. So it's going to have a bunch of circle edges and stuff. So we plug in x and y, the point in there, and that'll give us the slope at that point. And we can find an equation, which is what we're going to do with the next question. Example 2. It says, find the slope of the circle with center at the origin and radius 5 at the point 3, -4. Find the slope of the circle with center at the origin and radius 5 at the point 3, -4. That's all we're given. How do we find it? So we first have to have an equation. What's the equation we're dealing with? Find the slope. The circle. What's the equation of a circle? Yeah, a circle has this. There you go. It's x minus h squared plus y minus k squared equals the radius squared. Where's the center? The origin, which is 0, 0. The radius, this is the h and k value. The radius is 5. And so we have x minus 0 squared, y minus 0 squared equals 5 squared. So we end up with x squared plus y squared equals 25. That's just setting up our equation. We still haven't, now we gotta find the question, answer to the question of the question. What is the question looking for? Yeah, find the slope. There, find the slope. How do we find the slope? Yeah, because dy dx is equal to the slope. So we gotta take implicit differentiation. Actually, we can do it 2 ways. How would you all approach this? If you were given this, would you first solve for y and then take the derivative of it? Or would you just go ahead and use implicit differentiation? Use implicit differentiation. Yeah, yes, very good. We would use implicit differentiation because it's much easier. Because if we didn't, we'd have to solve for y, which would give us y equals 25 minus x squared plus minus the square root of it. We have to take the derivative of that, which means 25 minus x squared to the power 1/2. Take the derivative of all that stuff. It's a lot of extra work. Using implicit differentiation, what's the derivative of x squared? What's the derivative of y squared? 2y dy dx. And the derivative of 25? Right, I know you said 0. You were just not finished yet. So now we just have to solve for this, dy dx. So you got to move the 2x over. How do you do that? By subtracting 2x. So we have 2y dy dx is equal to negative 2x. Divide by 2y. And the 2's cancel. So dy dx is equal to negative x over y. So what's the slope? We know it's a circle. What's the slope? What's the final answer? Because we have our x and y values right here. Plug those points right there. Let's see the next one. Again, as I said, it's the algebra part of these things that are going to be the most time consuming. Because in calculus, it's just take the derivative of each term, move all the dy dx's to one side, non-dy dx's to the other side, isolate dy dx, and you're done. All right, let's look at example 3. Find dy dx of this function. And I included the graph because I thought it was a pretty cool graph. It's like somebody trying to draw an X during an earthquake. All right. So it's only asking us to find dy dx. So go ahead. All right. The derivative of y squared is what? 2y dy dx. Derivative of x squared, 2x. Derivative of sine is cosine. The derivative of x times y. This is my f, this is g. So derivative of f is 1. Derivative of g is dy dx. So it's y plus x dy dx. Now, because we have this in parentheses, we distribute it to get rid of it. So we have 2y dy dx. We have y cosine xy plus x cosine xy dy dx. Then what? Next step. Yeah, move the x cosine one to the other side. So we have 2y dy dx minus x cosine xy dy dx equals 2x plus y cosine xy. Now you can easily see how you can make mistakes here. Since we have all the dx dy's to one side, we go ahead and factor it out. Two y x cosine xy equals 2x then divide both sides. Can't go any further. Nothing can factor out. Nope. I'm going to ask you questions, but just to make sure you know. No, nothing, because if it was factorable, then it'd be the same in both of these terms. And that's the answer as far as we can go. What do y'all think? Getting a little easier now? This is a lot faster than, because now you have to worry about splitting up anything. Just take a derivative as it is and get the dy dx by itself. Now we're going to look at higher order derivatives. What does that mean? Taking this higher order derivatives, second derivative, third derivative, fourth derivative. We can keep on going infinitely, especially when we deal with trig functions. They never end. Oops, I get this here. So example 4. It says if 2x cubed minus 3y squared equals 8. What is this one asking for? The second derivative, right? The derivative of the derivative. And I'm glad you put it that way, because we have to make sure we look at it that way. It's a derivative of the derivative. So let's do each part. What's the derivative of this first part? 6x squared. And this one? Equals. What am I missing? Dy dx. Very good. You know, instead of writing dy dx, you can always put y prime. If that's too much writing for you, you can always put y prime. Or anything else. You could say that m equals dy dx and put m there instead. Because if you put y prime, then that little prime could get mixed up somewhere else. It could get mixed up with the y squared or y cubed. So you could do that type of substitution anytime, any place you want to. So what do I do next? Have we taken the first derivative yet? No, we haven't found dy dx yet. Why do I move that one over? I'm sorry. Why do I move this one over? Yeah, to make it positive. If not, it'll be negative, and I move that one over, it'll be negative. I gotta change all the signs. Huh. If this is negative, move it over. So we have 6x² equals 6y dy dx. Then divide by 6y. So now I can put dy dx is equal to the 6's cancel, x² over y. Now what? Now we take the derivative of the derivative. So this is our first one. So the derivative of dy dx is d squared y dx squared. That's the second derivative. Now we're going to take the derivative of this part, which will use what rule? Quotient rule. So we have x squared. This is f g. F prime is 2x. G prime is 1 dy dx. And we subtract. Since it's a fraction, we just subtract. 2x times y, so 2xy, minus x squared dy dx over what? Y squared. Whatever's on the bottom, you square it. Are we done? Is that the second derivative? Why not? Because what? Well, this is the second derivative. Don't we know what dy dx is? Yeah, so now what we gotta do is plug that in there. Because we can't have this inside there, because it means nothing to us. We have to plug that in there. So 2xy, it's x squared over y. That's what that is, over y squared. Again, now it's the algebra that's going to be hurting us. So we have 2xy over 1 minus x squared over 1 times, so x squared times x squared is x to the 4th over y squared. Because we have a fraction up on top. We have to get a common denominator. So this one has to get multiplied by y times y over y. 2xy squared over y minus x to the 4th over y squared. We have a common denominator on top. So we just worry about the top. So it's 2xy squared minus x to the 4th over y squared. A fraction over a fraction. So we take the top fraction and leave it alone. Multiply it by the flip of the bottom fraction to xy squared minus x to the fourth over y cubed. There is our second derivative. Let me see what the next one is going to be. Oh, yeah, look at your notes. Any questions about that one? So whenever you do higher order derivatives, you have to keep track of all the other derivatives that you keep, because for the third derivative, we're going to have to use the first derivative and the second derivative and substitute those back in there. Yes. Good question. Can anybody guess? Anybody take any physics courses here? Okay. Well, in motion problems, this I use is the most obvious one. In motion problems, you have a particle at rest somewhere. This is at t 0 equals 0. It doesn't move. Now, when this particle moves, after, let's say, 1 second, it's changed locations. That's what we call the position function, the displacement. It's pretty much just the position of the function. Now, how fast that changes. So from this point to this point, then from this point to this point, that's a change of positions. So that's what we call a velocity. This is the rate of change of the position function. As time moves on, the position changes. How fast is that position changing? That's what velocity is. Position function is just where it is. Now, how fast your velocity changes. So the velocity is the first derivative of your position statement. Because it's a rate of change, it's a slope, it's a movement. So the acceleration of this particle is the first derivative of the velocity, which is the second derivative of the position function. That's what acceleration is how fast is the velocity changing from period to period. So you have velocity 2 minus velocity 1 over t2 minus t1, or t1. That's acceleration. Velocity is s2 minus s1 over t2 minus t1. That's what velocity is. The slope of velocity of the position. And there's a third derivative. What about acceleration change? Can your acceleration change? Yeah, especially if you're a race car or a jet plane flying off a carrier or a rocket trying to accelerate out of the atmosphere. So we call that a jerk. This is the first derivative of acceleration, which is the second derivative of velocity, which is the third derivative of the position function. So the change of acceleration is a jerk, change of velocity is acceleration, change of position is velocity, and the position itself is where you all start. So there's one of the uses for it. And it's necessary if we want to do any space travel, if you want to drive your car, if you want to do anything that moves, that includes the motor in your car, all the pieces that move in there, all has to follow these principles, these laws. On your car, you have the tachometer. You read that little thing, it has 1, 2, 3, and it says times 1,000 or times 10,000. That's how many revolutions your cylinder, your crankshaft is turning to make your car go forward. The faster it turns, the faster you go. So again, all this stuff is angular momentum, versus linear, converting to linear movement. It's all calculus. This is why if you want to be an engineer, you have to know calculus. These are the tools you'll use. I'm glad you asked that question. I can talk about it all day. All right, so that was example 4. Now, if you look at your pictures, we have a curve. Some curve. At any point, what we've been finding so far is this line here. If a line touches a curve at one point, what's it called? This is called the tangent line. Perpendicular to the tangent line, supposed to go to that point. Perpendicular to that tangent line is what we call a normal line. Or it's sometimes called orthogonal, which means all they are here is if this slope is A, then what's the slope of the perpendicular line? -1/A. Perpendicular slopes are negative reciprocals of the other. Now, why is this important? Again, back to space travel. But funny, if this is the Earth's atmosphere, and this is you coming in the spaceship coming back from the moon, there's one point, actually, there's like a 7 to 8 degree change inside there that the shuttlecraft, the spaceship, has to approach and enter the Earth's atmosphere. Anything lower than this, it'll bounce off and never come back. You'll never get it back. If anything larger than that, you'll burn up in the atmosphere. You hit the atmosphere too fast, and the air molecules will just disintegrate your spaceship. So this is why you need to know this kind of things. So you see, at what point here you have the orthogonal, the normal curve, and then you see at what point, what is our landing trajectory? I'm glad they thought about that before the first flight. But how many of y'all think that air would cause things to burn up? If you ever went driving on the highway at 70, 80 miles an hour and stuck your hand outside, what happens to your hand? It gets pushed back, but then you feel that air on there. It makes it, well, because you're going that slow, it feels cold. But then when you bring it back inside, what happens to your hand? What does it feel like now? It starts burning up because now there's no more cold air blowing. It's now in the atmosphere inside the car. So that's what happens there is you have in the atmosphere, here's the Earth, here's the atmosphere of space. Air molecules are very dispersed. And then the closer you get to Earth, because air is a molecule. It has weight, it has mass, it has a dimension. So the gravity pulls it down. So as it pulls it down, it gets more compact. That's the reason we could breathe down here. That's why the higher you go in the mountains, Mount Everest, at a certain point at 10,000 feet, you got to start putting on oxygen because there's not enough air molecules for you to breathe. Airplanes, same thing. That's why after above 10,000, you have to have compressed air inside, or you have to have air circulating inside the cabin of the airplane because the molecules of air are so dispersed. So the higher you go, so as you enter from space, there aren't that many molecules. You start seeing a little bit of flames around your spaceship. Then the further you go in our atmosphere, there's more molecules. They collide with your spaceship, and there's a lot more friction from those air molecules hitting the spaceship. And then eventually what happens is you get to a very thick place and it just engulfs. And then you said, well, why doesn't it burn up? Or what happens to it? There's a small area here in the atmosphere that is coming down that it's so severe that the molecules bouncing off the spaceship are so thick, it's causing a fire around it that you can't communicate. Eventually, what all that's doing is slowing down your spacecraft. Remember, out here, it travels around 18,000 miles an hour. It's got to slow down to zero in less than 100 miles. And that's what happens. When it comes in at an angle, it slows down because of the atmosphere slowing it. And it gets to a point where it's pretty much nothing but free fall. It's no more, once the fire dies out, it's now just in a free fall. And that's when now you can open your parachutes. If you open it too soon, they'll just disintegrate and you end up like a Soviet rocket, and they land, they don't use parachutes. They bounce off the ground. And we're not that much smarter because we land in the ocean. And at 120 miles an hour, which is free fall, it's like hitting concrete. So there's no easy way of doing it. Now they're having the re-entry rockets you can land, which is fabulous. I mean, having these rockets that'll come out from space and land back on Earth. Controlled landing. That's amazing. Anyway, I'm sorry about that. So that's what normal curves are. So once you find the slope, the derivative, you can find the slope of the normal line to it, the orthogonal slope. Orthogonal, they also call it orthonormal, which is why they call it normal. And then the other picture I put in there is, for example, 5, is the folium of Descartes. A folium is any graph that looks like that. It's just in the first quadrant, it looks like that. And the beautiful thing about that is that everywhere you look at it, there are the slopes changes, and what you're really doing is you have different functions here because it changes from here to here, from here to here, it changes, and then from here to here. So you really have 3 different functions that you're looking at. That's the folium of Descartes. He thought about that. And Descartes is the guy who came up with the phrase, I think, therefore I am. Cogito ergo sum. So that's a small little free information. Example 5. Where is it? Okay. Example 5. Show that the point 24 lies on the curve. Ooh, that one didn't come out. X cubed plus y cubed minus 9xy equals 0. I don't know why that didn't come out. So let's first find that. Then find the tangent and normal lines to the curve at that point. So how do we prove the first one? How do we prove that this point is on this curve? Plug it in. Because if we plug in the values and it equals 0, then it's on the curve. So this is part 1. So we get 2 cubed plus 4 cubed minus 9, 2 times 4. So work it out. What do you get? What is 2 cubed? 8. What is 4 cubed? 4 times 4 is 16. 16 times 4? 64. 9 times 4 is 36. 36 times 2. 8 plus 64. So the 0.24 is on that curve. That's good. Now we got to find the tangent and normal lines to the curve. We have to find the equations of the line. How do we do that? Part 2. Find the equations of the tangent and normal lines at the 0.24. So what do we have to find first? What do you need to find the equation of a line? To find an equation of a line, you need a point and you need a slope. Do we have those? Do we have a point? Yeah, the point is 2, 4. Do we have a slope? Can we find the slope? Yes. So how do we find the slope? Take the derivative, because the slope is dy dx. So let's find the slope. Derivative of x cubed. Y cubed. Then we have f is 9x. G is y. Minus f prime is 9. G prime is dy dx. Equals 0. What do I do next? Can you have parentheses in your equation? No, we have to get rid of the parentheses. So we have to distribute that negative sign. Put 9y. And then what do I do? Yeah, dy dx to one side and non-dy dx to the other side. So since that one's positive, that doesn't matter. Let's move, since this one's squared, let's do that one there. Let's move the 3x squared and the 9y to the other side. Next step. What's my next step? Yeah, factor out the dy dx. Okay. Can anything factor out of these equations? They both are factors of 3. So we can take out a 3 out of the top, which makes it negative x squared plus 3y. We can take out a 3 out of the bottom. The 3's cancel. So now what do? I have my slope. Now what do? Is that? Well, do I know the slope? It's the slope at that point. Let's plug that point in. This is the x and this is the y. So we have dy dx equals negative x squared plus 3y. Y squared. So I have dy dx at negative 2 squared, 3 times 4, 4 squared minus 3 times 2. So 12 minus 4 is 8. 16 minus 6 is 10. They both have a 2 in common. So the slope, so dy dx equals 4/5. That's just plugging in numbers. Now what do I do? What does this number tell me? The slope of what? Is what? Okay, this is slope at the point of what? What line?
This.
It's the slope of the line tangent to the curve at 0.24. This is equal to the slope of the line tangent to the curve at the point 2, 4. So what do we do with that now? What are we looking for? What's our question looking for? The equation of the tangent line. So how do we find the equation of the tangent line? Well, this is the form we want. No. Do we have y? Where? It's 4. Do we have m? Yes, it's 4/5. Do we have x? Yes, it's 2. Only thing we don't have is b. So since we have equal sign in fractions, nothing cancels. Get rid of the fraction. Find the LCD. What's the LCD in this example? What we have here is 8/5 plus b. 5 is the only denominator. It's the only denominator, it's 5. That's the least common denominator is 5. Multiply each term by the LCD. Each term. So 5 times 4, 5 times 8/5, 5 times b. Third step. Reduce. Cancel anything you can. The only thing you can cancel is this 5. So we have 5 times 4 equals 8 plus 5 times b. Multiply to remove the parentheses. 20 equals 8 plus 5b. And solve. Solve for b. Subtract 8. So b is equal to 12/5. We know our slope was 4/5. Put those in here. Y equals 4/5x plus 12/5. That is the equation of what? That's the equation of the tangent line. We're also supposed to find the equation of the normal line. How do we do that? How do we find the equation of the line normal to that curve? Okay, part 3. Find the equation of the line normal to the curve at 2, 4. Remember, since we're looking for equation of a line, we need to have a point and a slope. Do we have the point? Yeah, it's 2, 4. Do we have the slope? What is it? Minus 5/4. Because what we had originally is the slope of the line tangent, which is 4/5. We need the slope perpendicular to it, which is the negative reciprocal. The perpendicular slope is flipping it and change the sign. That's all it takes. So now we have the slope and we have a point. We got to find the equation. 4 equals negative 5/4 times 2 plus b. The 2 and the 4 cancel. Negative 5/2 plus b. Everybody okay with what we're doing so far? So the tangent line, the slope of the tangent line is the first derivative. The normal slope is the flip negative, change the sign and flip it. And the rest of it's the same. Multiply each term by the LCD, which is 2. 2 times 4 is 8. 2's cancel. Negative 5 plus 2b. Eight plus 5 is 13. B is equal to 13/2. And our slope was negative 5/4. Equation of the line normal to the curve at 2, 4. Oh, that's the last one. Oh, I thought we had 2 more. So needless to say, we won't do the next section. What do y'all think? Implicit differentiation to me is a lot more interesting than explicit differentiation because you can do a lot more with it. You're not limited anymore. So what are y'all gonna do over the break? If you think about it, all we have left to do this semester. One, two, three, four, five. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have 15 topics and 16 class periods. Because we're only finished the first half of the semester now. We have 8 weeks once we come back. So, yeah, we're not going to be hurting for time. But as you see, the further we go down, like the Newton's method and some other ones of these we'll look at are going to deal with called iterative methods, which we start off with an initial guess and then we keep on repeating that process until we get close to an answer. So you have to know all these processes to be able to do this stuff. I need everybody to be caught up when we come back from spring break. Because we're going to finish up the chapter, related rates and linearization. And then we start more application problems. Mean value theorem isn't going to take that long. Monotonic functions and first derivative test, concavity. Chapter 4 really shouldn't take that long to finish. At least I'll say up to this stuff here, we can easily, actually, I think we can even do in one day. Because it all builds on itself. The concavity and curve sketching, monotonic functions, first derivative tests, they follow each other. So it's just straightforward. Extreme values on closed intervals, mean value. You guys can do this. So I'm really not worried about the rest of the semester. If we need to, we'll take some time off so y'all catch up. But remember, if we take off time in the beginning, then we won't have time to give any more extra in the end. So I need you guys, I hate to say it, is during the break, please try to do your work.